Okay, so let's talk about open problems, future, all of that, right? So I have a bunch of things here, and I think we should be able to hit all, but let's start from the beginning. So we are going to talk about several of these aspects here. As you can see, a lot of these areas are still active research directions, including coming up with new post-hoc explanation methods which sort of alleviate or address some of the limitations that we have talked about, right? So we'll go in this order and try to cover each of these pieces one by one. So the first, the first one is, new methods for more reliable post-hoc explanations, right? Not surprising because we are seeing there are all these problems with existing methods. What do we do? Okay. All right. So we have seen that there are several limitations in the behavior of existing methods. For example, they're unstable, inconsistent, fragile, not faithful. While there are already different attempts to address some of these limitations, there is definitely more work that is needed, right? So for example, I'm going to touch upon one recent approach that we had, which gained a lot of traction, which helps address some of the classic issues with these post-hoc explanation methods. Not all of them, some of them. So we talked about, methods such as LIME being unstable. And we also talked about this issue of consistency, which is, the same method run on the same point can generate drastically different explanations. And that is particularly true when the number of perturbations you're using is small, right? So we discussed this issue a little bit, that if it's the problem with having too few perturbations, what is the optimal number of perturbations? Can we just use a very large number of perturbations, right? The issue with using very large number of perturbations is, again, it's a computational challenge in practice. Because especially if you're looking at very complex models like InceptionNet or ResNet and so on, querying these models for labels repeatedly for a lot of points, because each time you generate a perturbation, you go and take the label from the model. And if you keep doing this repeatedly for a large number of perturbations for each point in the data set, this becomes very computationally intensive very fast, right? So because of that, you can't just apply the principle of just put a large number of perturbations there and you'll be done. So a more saner approach would be to actually determine what is the minimum number of perturbations required to get to that sort of converged explanation, okay? So what we do is this kind of idea or paper on explanations with some uncertainty guarantees. So we consider Bayesian versions of LIME and SHAP. And the reason why this is actually better than just having point estimates of feature importances is it at least tells you what is the confidence interval or the uncertainty interval associated with your explanations. This is particularly important because, as we have seen, there are not exactly very authoritative metrics for things like faithfulness. I mean, there are ways in which we discussed how they can be approached, and you can compare two explanations and so on. Given that that piece is not completely set in the literature yet, this kind of having some estimates of uncertainty, instead of giving 1 point estimate, 1 point value for each feature and say this is the importance, if we can say how uncertain the algorithm is about this feature importance, that can be very valuable, right? And this also kind of helps us consolidate. Like, for example, there was a nice point about if you change the number of perturbations, your explanation changes, right? And as an end user or even as a designer, it makes no sense to me if I see two different explanations and I don't know how to consolidate which one is right, all of that. But once you put uncertainty into the picture, if I run LIME with, say, 100 perturbations, versus running LIME with 2000 perturbations. So clearly the mean has changed, but the uncertainty interval is still being captured, right? So with lesser number of perturbations, I'm seeing that there is more uncertainty. With larger number of perturbations, I'm seeing that there is less uncertainty, but at least it's captured by this window. These are not conflicting things, right? So that is helpful for me to sort of consolidate what is happening here, okay? What we do here is essentially this kind of a Bayesian locally weighted regression. So we make the entire setup of LIME Bayesian pretty much. And we make it in such a way that you don't have to use methods like sampling or variational inference or anything which is computationally intensive. We can compute all the parameters in closed form. And the means of these approaches also turn out to be the estimates that LIME or SHAP will output in expectation. Okay, so there's a clear parallel, and we are able to add an uncertainty interval on top of it. And using some of these Bayesian frameworks that we have, or the details of this framework, we also developed like some theory for like estimating the required number of perturbations that will help us achieve user-defined levels of confidence. So for example, if a user says, I need an explanation where the true feature importance lies within plus or minus 0.5 of your estimated feature importance with 95% confidence interval. If that's the requirement of a user, we can take those and then give you a number n, which is the number of perturbations that you need to use with BayesLIME or BayesSHAP in order to give this guarantee on the uncertainty of the feature importance values. Okay, and we can also do more tweaks in this kind of a setting because we are capturing uncertainty. For example, instead of sort of just taking random perturbations, which is what these approaches do, typically we can be sort of more intelligent about it and say we'll only choose those points that the learning algorithm is most uncertain about, because we are capturing the uncertainty now, right? And only on those points we'll ask the underlying models for labels. For other points which your learning algorithm is already certain about, we don't need to query this complex model and waste compute in that. Okay? So yeah, that adds to the efficiency. So in some sense, this whole approach allows us to construct explanations with user-defined levels of confidence in an efficient manner. Okay, so other questions that would be interesting to explore in this kind of a context is, can we construct post hoc explanations that are provably robust to various adversarial attacks discussed earlier, right? So what the previous approach that I talked about is fixing is some pieces, some of the consistency issues and so on, but can we now develop new methods or new explanations that are provably robust to some of the adversarial attacks we discussed? Or can we construct post hoc explanations that can simultaneously guarantee several of the properties that we discussed, which is whether it's fairness or faithfulness or stability and so on? There are no answers for these questions at this time. Okay. All right. Let's talk about what are some problems that are open in terms of theoretical analysis. So we actually discussed some of the recent theoretical results just like a few minutes back. Despite some of those preliminary attempts, of course, there are huge gaps. There is a lot more to do. For example, can we characterize the conditions under which post hoc explanation method unsuccessfully or successfully captures the behavior of the underlying model, right? Currently, there are not very good answers for this, but like, can we put a precise characterization on when they can actually capture the underlying model or not, with respect to different notions of what exactly it means to capture the behavior of an underlying model, right? And given the properties of the underlying model, data distribution, can we theoretically determine which explanation method should be employed, right? So some of our recent work is going along these directions, but it's no way sort of a solution to these kinds of big questions. But it's interesting to sort of think about these kinds of questions, right? And can we theoretically analyze the nature of the prototypes and attention weights learned by deep nets with added layers? When are these meaningful? When are they spurious? Again, there are no answers. These are all big open problems, and they're also not easy problems in some sense, but definitely worth exploring. Okay, so let's talk a little bit about what are some other open questions in empirical evaluation of the correctness and utility of model interpretations, right? So we actually spent quite a bit of time discussing some of the empirical results and analysis of correctness and utility. In spite of all that, as we briefly talked about earlier, there is no clear characterization of which methods, if any, are correct or useful under what conditions, right? Again, this is something that I think hopefully as the field also evolves, we come up with like a certain systematic set of evaluations, benchmarks, standard practices for doing user studies, and then we'll be able to come up with more clearer answers. But currently, if you say, oh, when does, or like, is LIME explanation or are LIME explanations helpful to doctors in this? The answer is we really don't know, right? And there is actually even lesser work, I'm sure some of you have noticed this, but there is even lesser work on the empirical analysis of the correctness or utility of interpretations generated by inherently interpretable models, right? Post hoc explanations, there has been a huge sort of, like area that has formed around it, but inherently interpretable models, there is even less work. For example, are prototypes generated by adding these layers even meaningful? We don't know, right? Can they be leveraged in any real-world applications? What about attention weights? There are absolutely no studies to answer any of these questions. Okay. All right. So the next piece is characterizing the similarities and differences. We talked about how a lot of these methods actually disagree with each other in terms of the outputs they produce, right? But let's see what are some open problems to look at there. Okay. So several post hoc explanation methods exist, which are employing diverse algorithms, diverse definitions of what even is an explanation. Right? Some are saying, rules is an explanation, others are saying importances are explanations, and so on. So under what conditions do these methods, or a subset of these methods at least, generate similar outputs, right? So we want to try and quantify that, and that will also help us understand when will they give you similar outputs, when will they give you different outputs. That understanding is also important for us to sort of both build better methods and like basically get to a point of where we know a bit more than what we know about explanation methods currently, right? And there are multiple interpretable models which output, natural synthetic prototypes. When are these actually generating similar prototypes? And why, under what conditions are they generating similar prototypes? When are they going to generate different prototypes? Again, we don't know, right? So clearly, I think that's whole space of making models interpretable by adding layers of prototypes or attentions is like there's a huge void in terms of what can we say theoretically at all, or even empirical analysis, to be honest. Okay, and then the next piece is, so today I think in this discussion we have extensively covered predictive models, specifically focusing on classification. Now, what do we do about going beyond classification, right? I think our immediate reaction is, well, classification is already messy enough, so what can we do beyond it? But I think there is no harm in hoping and dreaming anytime. So yeah, now, with sort of this craziness of more and more complex models kicking into full force and high gear, so now we have all these large language models, foundation models. Like, what does it even mean to think of interpretability there, right? So what's even feasible there? Those are also like just open questions that nobody has good answers for, right? And there's also already active work on interpretability in reinforcement learning and graph neural networks. So however, there is very little research on analyzing the correctness or utility of explanations in these contexts. So currently there are some approaches laid out there, but like nobody really knows if they're doing the right thing, if they're right, when are they right, all of that. Okay. So given that these primitive interpretable models or post hoc explanations themselves suffer from so many limitations, how do we ensure that when we try and construct explanations for more complex models, those are probably going to be more reliable and they're not suffering from all these limitations that we have just spent the last couple of hours talking, right? Okay. So another sort of, these three are kind of related, but essentially exploring intersections between interpretability and other key pillars of this broader area of trustworthy machine learning, like robustness or fairness or privacy, is also very important, because there are implications of interpretability on these properties, and there are also implications of these properties on interpretability. So how to sort of think about that, that's also like a space where there are lots of interesting open problems. Okay. So for example, if we think about robustness, we'll sort of we can say, are inherently interpretable models with these prototype or attention layers more robust than those without these layers, right? If so, why? Are they giving, I think, earlier we were discussing with Anthony that are these layers actually adding some kind of regularization? If so, can they improve robustness almost as a side effect, okay? Again, we don't know, so that's a problem up for exploration. And are there any inherent trade-offs between certain kinds of model interpretability and model robustness? Or do these aspects always kind of try and reinforce each other? Again, an open question. So some of our recent work actually shows theoretically and empirically that counterfactual explanation generation algorithms actually output adversarial examples. So this is pretty interesting because essentially, as we talked about earlier, a lot of these algorithms are basically saying, take a point, perturb it slightly, get it across the boundary, and that is your counterfactual, right? But that's also kind of what a lot of adversarial example approaches do. Okay, that's one part of it, but there is the other part of it, which is a lot of machine learning community is trying to build adversarially robust models, which is they're trying to eliminate adversarial examples. So now what does this mean for counterfactual explanations or recourses? So where does the boundary of, or where does the end of counterfactual explanations happen and where does the beginning of adversarial examples happen, right? So what is the boundary between those two? That's also quite blurry. So I think there is a huge sort of set of research problems there. Okay, so with respect to model fairness, in fact, this is yet another interesting piece. Oftentimes when people motivate model interpretations or explanations, they think of it as, oh, explanations can help unearth all these unfairness or biases in models, right? So that's like a motivation that's often used in the introductions of a lot of papers. However, there is not a whole lot of empirical or theoretical research which actually kind of touches upon this topic. Forget demonstrating it, we don't even have studies that sort of try to see if this is happening, right? So definitely conducting more empirical evaluations and user studies along these lines to determine how interpretations and explanations can complement statistical notions of fairness in identifying biases is important. Because there is already a bunch of literature on fairness, but that literature focuses on how to sort of quantify statistically what unfairness looks like. The argument for explanations is when you can't really clearly quantify what fairness looks like, that's when explanations can help. But that said, there are not many studies which actually show what are the complementary capabilities of explanations or model interpretations in detecting such unquantifiable notions of what unfairness looks like, right? So there is again a big gap there. And how does the fairness, the statistical notions of fairness of inherently interpretable models compare with that of vanilla models, right? So for example, if I just train an uninterpretable model, how does the fairness of that model, whether it's equality of opportunity or whether it's statistical parity, how do those properties compare with the fairness of a model that is inherently interpretable? Either things like rule lists or either when you're adding prototype layers or attention weights, how to think about those, right? And are there any inherent trade-offs between certain kinds of model interpretability and model fairness, or do these aspects reinforce each other? Again, that relationship or connection is unclear. Okay. All right, so privacy, this is actually something that has come up during the break, and I was talking to somebody that I now can't recall. But essentially, I think by definition, a lot of model interpretability and explanations is about exposing information about the model, right? So how can these aspects, or can these model interpretations and explanations expose sensitive information from the data sets? For example, right? Again, there is very little research. I think barring a couple of papers, there is not a whole lot of work in this area. So there is very little research on the privacy implications of interpretable models or explanations. So what kinds of privacy attacks are enabled by providing model interpretations or explanations? Again, we don't have very clear answers, right? And furthermore, I mean, we don't have answers to that, which means we also don't have answers to this, which is, do differentially private models actually help defend against such attacks? If so, under what conditions do they help? Should we actually construct differentially private explanations in order to mitigate these kinds of attacks? These are all open problems. All right, okay, so the last part, we have thought quite a bit about, model interpretations, explanations, and so on. And we have sort of gone into the depth of, what their weaknesses are, how to think about this, connections, all kinds of stuff, right? And in the process, I mean, while there are limitations of these approaches, there is nothing that stops us from thinking about new tools, interfaces, which can be sort of used to make models more interpretable or to facilitate model understanding, right? So for example, while APIs and commands and visualizations are probably natural to some of us, like for example, people who are maybe more ML savvy, they may not be as natural to say somebody like a policymaker or a doctor. So what can be some new tools, visualizations, interfaces to sort of help them understand what models are doing, right? So that is also an important area of research which I think needs to receive more attention. And of course, standardized benchmarks and tools are also important for us to develop some common understanding of like where we are as a field, right? Okay, so the first question under this broad direction that I put together is, can we construct more interactive interfaces for end users to engage with models, right? Like instead of giving them, here is your LIME explanation, take your future importances, and this is what I can give you. What if we can make this process more interactive? What would be the nature of such interactions, right? So this is something that we have been exploring with some students recently. I'll show like a quick demo. Hopefully that should work. Let's see. Okay. So for example, so this is basically a tool that we developed called Talk to Model. So you can use natural language interface and chat with models. Like this is literally like chatting with models to understand how it's making predictions, right? So for example, what are the predictions on people over 20 years? Okay, so it's saying, for data with age greater than 20, the model is predicting this. And if I say explain predictions for people over 20 years, it kind of shows me what are the important features and so on, right? And I can ask questions and so on and so forth. So this kind of interface is more natural. And the reason why we build such an interface is that when we work with hospitals and so on, we often get a request, like a feature request from a lot of these people that like the current ways in which UML people give us these tools is so clunky. You will give me 5 feature importance values and you expect me to just deal with it. Like I want a more natural way of engaging with the model. And one of the practitioners we were interviewing once was like, I just want a natural way to talk to the model, right? And from that is born all this entire endeavor, but okay. So yeah, I mean, I'm not saying that's perfect, but like essentially we need to keep thinking about more interactive interfaces, which can make this process of understanding models more natural, right? And as model interpretations and explanations are employed in different settings, we need to develop new benchmarks and tools for enabling comparison of various properties of these explanation methods or interpretation methods. How do we sort of enable that? Because I think we can't use a single benchmark for all possible application settings. So how do we make the process of creating multiple benchmarks easier? So that's also something we need to think about. Okay, so with that, I think we are almost coming to the end of this discussion, a little earlier than planned, but I think that's good. I'm sure all of you also want to take a break and go home and do other things. So there has been a lot of renewed interest in model understanding over the past half a decade or so, right? And a lot of this has come from this aspect of ML models being deployed in a lot of healthcare and other high-stakes settings, right? So that's when, because of that happening, there has been a growing interest and seriousness in thinking about, let's understand models, let's understand the predictions they're making, right? And as these models continue to get more and more complex and they continue to find more applications, the need for understanding what these models are doing is only going to raise. And I can say that, especially given the legislations and regulations that are also being pushed from different quarters, both in Europe and US, I think the need for model understanding is going to become a real requirement in practice also in several domains. Okay? So as we just saw, there are like several interesting open research problems, and there are a ton of them, and what we just saw is probably a subset of them, but essentially the field is sort of wide open to be explored and sort of like open for us to basically develop a new understanding of what we have today, where are the gaps and how to improve, right? So the thing that I really like about the field of explainable AI is that you can approach this topic from a lot of diverse perspectives. Whether you're a theoretician, whether you're an ML algorithms person, whether you're a HCI researcher or an interdisciplinary researcher, there is definitely room to contribute from all of these sides, as probably this discussion and this talk has already convinced you, right? And in fact, I'm somebody who likes to sort of move around some of these areas. So I feel like this area of explainable AI is like a perfect ground for somebody like me who likes to do theory, develop methods, and also do some user studies and interdisciplinary work. I get to exercise like different aspects of those. Okay, so with that, I think I'm going to pause here. We are at 3:45, and I'm happy to take more questions, address any other comments, and so on. And before we do that, so this is just like a bunch of useful links, course on this topic, a bunch more tutorials on this topic, and Trustworthy ML Initiative also has a bunch more resources on this topic.